In this case, we will be setting up the curve. We have a 20mm calibration block with a single hole. There are also 40mm calibration blocks. The standard ones are 20 and 40mm. There are even larger ones. Usually it's 40mm. There's a hole on one side and on the other side as well. They will be at different heights. Or there are larger calibration blocks which have a lot of holes. In this case, we will calibrate the DAC using a single 3mm drilled hole. The first signal will go straight, meaning we fire, the beam goes from the center and hits the hole. Into the hole, and the second signal will be reflected from the bottom. It reflects and hits. The third will be the third signal. It will go down, then up and hit the signal. And the fourth, in this kind of zigzag way, we will set up the points. The first point is at 45 degrees like this, and here we have the 60-degree probe. We find it, we find the beam, we roughly find the maximum amplitude, and the maximum amplitude is shown on the monitor here. It shows it approximately like this. So, in order to double check, we take a ruler and observe what is actually being shown. The monitor itself clearly shows that diagonally it's 21 millimeters, depth is 10.5, and the distance that we set up X valve is 55 and 9. So from the beginning, from the start of the probe, it's 5.9, 6.6 millimeters. This is how we check that we have 6 millimeters and 6 millimeters. It lines up exactly. It matches here. So that's correct. It means we found it correctly. And as for the depth, we trust what it shows. Right here it shows about 10 millimeters. So we found the first point correctly. Now, using next group, we find the ducts. We found the ducts and we press setup in the setup menu. We set it up as custom. Reflex is on. Okay. So we exit, set the first point, found the maximum response. Set it at 80% of the monitor, add the first point, one added. Now we'll look for the second point. So we have the first loop that is from the middle. So our X file turned out to be 13.2. Here it precisely hits this specific distance, and we have carefully fixed it right here. The measurement is 21.2 millimeters diagonally, and the depth is exactly 10 millimeters. It clearly shows 10.6 millimeters. Yes, here it is, precisely 10.6 millimeters. And from the very start of the probe's position to the actual defect itself, the distance is 6 millimeters. To find the second point, we need to move and watch the monitor. We'll see it. Here, the second point appeared. We need to relocate and adjust the main gate, and then ascertain what this specific location or area is. That is, if we press gate several times, we'll see what this point is. Since we see it, we move it further. This is the width. If we press again, the level is set to 40%. Gate is set at 40. So we use gate, check what the signal is, and leave it at 80%. Monitor. It shows us a depth of 11 to the defect 36 millimeters, and we measure up to 36 millimeters, depth 11. To know the precise and exact depth, we absolutely definitely need to properly set the height of the calibration block. Otherwise, it will show the depth incorrectly. So we go to basic, press here, and look. Here is the bus bar collector. The block thickness is 20 millimeters. With U, it's 12.3, 60 degrees. We go back to the DAC. DAC, we're back. We set up the second point, 1. Here the second one is set, it will be approximately here. Now I'll show you how it shoots. The signal goes from here downward. Why will our first signal not match? The first depth was 10.6. This is 11, because at this moment it's shooting from below. That's why there's such a discrepancy. It detects the defect because the reflected signal comes from below, so the height will be slightly greater. We find the maximum amplitude. Let's set it to precisely 80% of the entire monitor's display area. That is, 2F Auto XX is now correctly set, and we will thoroughly double check everything once again to ensure accuracy. The distance from the defect to the start of the sample shows 41 approximately and just under 40. And on the monitor, we also see a depth of 40.2. At the moment, it's still 967. We record it, we record the second point and press ADD. We've added the second point. Now we look for the third point. The third point will be even further. On the monitor, we find 3. Here it is. The third distinct signal has clearly appeared, and now we will carefully measure this particular signal. Let's meticulously observe. Let's truly see what precise information it shows us. So, we will press the gate button and then carefully move the gate control and find this point. This little arrow here shows that we are measuring this exact point. That's what it's indicating. From the start of the sample to the defect is 70 millimeters. We measure, check, yes, 70 millimeters. Everything is correct. We've got it, and in the same way we can see. Here, L3 has passed. If it's L2, then the second echo signal, which means it's correct. And the depth shows 7.65. Now we'll adjust it, find the maximum amplitude so that for now it's at 10 millimeters. We set it to about 80% of the monitor. Find the maximum amplitude again at 80. There, 80% monitoring. We double check again. The depth shows 8.61. Because the farther we move away, the farther we shoot, the greater the margin of error becomes. We double check. 70, about 2, and that's what it shows, yes, and the depth is 9. So, if we measure from below, but it's going to shoot from above, right? About 9 millimeters, we can adjust it again, check if we found it exactly. The maximum might change just a little bit. It shows 8.5, that's good. We set the third point, add. Next, we move on to the next signal. We won't have enough monitor, so we need to increase the range. We go through next group, looking for where we have it. So we find basic. Here, the range is 125 millimeters. That means we see a signal at 125 millimeters. At the moment we have 97, so now we'll just increase it. Let's raise it to 100. We take Q like on block and look for the next signal. So we found some signal. Let's double check it. Let's see what kind of signal this is. We'll move the gate and check the signal. It shows us that this is the fourth reflected L4 and that the distance to the defect is 106 millimeters. We take a ruler and see that yes, it shows us about 106 and the depth is 11.4. So we set the monitor to 80%, find the maximum signal, set it to 80%. So that's the maximum. The display shows a depth of 10.6, distance 107. Let's double check the distance. The distance shows 107, and for us, that's about right. So now we mark the next point, number 4. We've marked it, and so on. Next, we can continue with 5, 6. At this point, we'll stop and press Done. Here we have formed before Krivaya. Now, if we see a very small signal, since when moving away, the signal will show small, but its decibel level will still be around 0. If we take, I'll try to explain, if we take the first signal, which we found here, we need to widen the gate to make it more convenient for us. So we press gate, press it again and increase the width. So first we move it to the beginning. And increase its width. Here white. And now our first signal will show here we've reached 0 practically. It shows us that the depth is 10.6 millimeters. The distance here is the depth. If we measure, it's about 10 millimeters here. And the distance shows us to the defect is 6 millimeters. That is, from the beginning to the defect, it is exactly 6 millimeters. 21 millimeters is the oblique line from where it shoots. The middle will be 21 millimeters if measured. At the moment we see that the decibel is minus 0.4. That is, this means that in decibels, 0. It possesses a defect which is located at a precise depth of exactly 10 millimeters. It will be exactly 3 millimeters. If this defect is embedded deeper, that is, it does not matter that we now see the reflection, we simply move away, and it is considered to be deeper in depth. The defect is deeper, will be viewed on the monitor. Here, in this case, minus 3.5 dB, we can reach 0. 0, this will mean that the defect is deep. In this case, we see 839. But if our metal thickness, instead of setting it to 20, we set it to 60, as we are about to do now, it will show a different depth. We go to basic, set the precise depth. Now we'll simply just change it to a very, very thick metal, for example. To 100 millimeters. Our depth is, let's assume, so we need to move the gate so that it doesn't pick up an unnecessary signal. I carefully reduce the overall width, and it clearly shows us the significant depth of the actual defect. 50 millimeters at a depth of 50 millimeters. Defect. So is it possible to find out what will happen? 0. We'll catch decibels. Here it is approximately 0 decibels. Yes, here is 0. At a depth of 50 millimeters. The distance to the defect is 75 millimeters. Let's check. Yes, indeed, 75 millimeters. That will be the depth. Since it is now clearly reflected, we can observe that the overall total depth will be precisely 50 millimeters. Furthermore, it will measure exactly 100 millimeters when measured diagonally across its full extent. Now, what we truly need to meticulously set up next is the crucial acceptance level and the comprehensive review level. That is to say, we absolutely need to go in and carefully find the precisely right one. Find it in the setup. Set it as much as we want. 4. We are considering additional curve levels, and for each of these distinct levels, we meticulously set the following parameters: 1 plus 6, then 2 plus 12, and finally 3 minus 6. 4 minus 12. Next, we exit, and now we can already see. In other words, we will automatically see in which area we need to work. So, if the signal reaches minus 12 or minus 6, we already consider minus 12. Everything depends on the acceptance level, which will be described in the procedure. What acceptable standard criteria will we have? They must be recorded and we have to check them. So, then we look. If we find an indication, we keep looking, keep checking. Specifically, for example, this is an indication. Here we have a reading of minus 8, so we already know that at a depth of 30 millimeters, the indication is about a 3 millimeter defect.